Hello everyone, welcome back to the channel. So today's LeetCode question 3558, number of ways to assign edge weight 1. It's a medium level question. Okay, let's go through the problem statement. So we have been given an edges array from which we can generate a graph like structure like this, where 1 is the root node of the graph. Okay, and what we have been told is we can assign every edge with the weight of 1 and 2. And what we need to do is we need to choose a node at the maximum depth, and our goal is to check in how many ways you can assign weights in the path from 1 to the maximum depth node such that the total sum of the path will be an odd number. Okay, consider this example. Here 4 and 5 are the nodes which are at the maximum depth. Consider we take the node 4. Okay, then the path will be 1, 3 and 4. Now we have been told that we can assign the weights as 1 and 2 only. So in how many ways we can get the total value from 1 to 4 as an odd is, we can assign this edge as 1 and this edge as 2. We get 3 as the answer. Or we can assign this edge as 2 and this as an edge as 1. We can get 3 as the answer. So there are two ways. Okay, let's go through this example. 1, 2, 3, 4. Here 4 is the node which is at the maximum depth. Here there are 3 edges, 1, 2 and 3, and each edge can be assigned 2 values, 1 or 2. So for any edge we have 2 values, right? So like the total number of possible values are 2 to the power 3, which is 8. So there are 8 total combinations that can be applied from 1 and 2 for all these edges, which will, and this combinations will include even combinations and odd combinations, odd pairs, right? The sum which is giving even and sum which has been given as odd. Now what we need to do is we just need to get the odd pairs. Now I have written all these 8 combinations here. Okay, so whenever you need to find the number of odd value, like we need the sum as odd, then what must we must have is that there must be odd number of integers here. So consider here there are 2 even numbers and there is one odd number, so we get then an odd answer. There are 2 even numbers and one odd number, so we get odd answer. Similarly here there is one odd number, okay, then one odd answer. Here 3 odd numbers, so we will get odd answers. So the total number of odd answer is equal to 4. Now if you see, the total like even plus odd was 8, and the total number of answers which are giving odd as the answer, they are 4 only, right? So it's just 8 by 2. So what we can see is if you have all these combinations, then the total number of odd combinations will be 2 to the power n by 2. Okay, so we can just write the formula. If we have k edges till the bottommost node, then the answer will be total assignments, which is 2 to the power k by 2 is equal to, which is 2 to the power k minus 1, and percentage is mod. Okay, let's go through this concept of binary exponentiation. Okay, so when you want to calculate 2 to the power 16, what you can do is 2 into 2 into 2 up till 16 times, right? But what if you are being asked to calculate 2 to the power a billion? Okay, then you can't do 1 billion calculation, right? This is a very bad. So there is this technique, binary exponentiation, which solves this problem in order of log n time. Okay. Now consider this: 2 to the power 1 is equal to 2. 2 to the power 2 is equal to 4. 2 to the power 4 equal to 16, and 2 to the power 8 is equal to 256. We know all these things, right? Now, if you see how is 2 to the power 2 calculated, 2 to the power of 2 can be calculated by squaring 2 to the power 1. 2 to the power 1 square of 2. 2 to the power 4 can be calculated by squaring 2 to the power of 2. 2 to the power square of 2. 2 to the power of 8 can be calculated by squaring 2 to the power of 4. You can look here. Okay, now consider you have been asked to calculate 2 to the power of 13. Now 13 can be represented as 13 equal to 8 plus 4 plus 1. So 2 to the power 13 can be represented as 2 to the power of 8 plus 4 plus 1 equal to 2 to the power 8, 2 to the power 4 and 2 to the power 1. Now we have seen that from 2 to the power 1 we can calculate 2 to the power 2, and from 2 to the power 2 we can calculate this 2 to the power 4, and from this we can calculate 2 to the power 8. Okay, so the entire technique is very simple. We don't calculate the exponents directly, we break the exponents in the power of 2. Like 13 can be written as 8 plus 4 plus 1, 19 can be written as 16 plus 2 plus 1. So 2 to the power of 19 can be written as 2 to the power of 16 into 2 to the power of 2 into 2 to the power of 1. Now let's see how bits come into the picture. Now the 13 can be broken down as 1, 1, 0, 1, right? And if you see here, 1000 is 8, 100 is 4, like, and 1 0 is 2, and like this is 1. Okay, so when what we can decode from this is 13 can be represented as 2 to the power of 2 to the power 13 can be represented as 2 to the power 8 into 2 to the power of 4 into 2 to the power of 1. So whenever a bit is set, we can just like add that thing to our answer. So if you found a set bit, add that power to the answer. So 2 to the power 13 can be broken down as like this. Like this bit is set, so we can add 2 to the power 1 here. Like this bit is not set, so we don't need this. So 2 to the power 2 will not be of any use. This bit is set, the 4 is set, so we add 2 to the power of 4. This bit is set, the 8 is set, so we add 2 to the power 8. Now in the final answer will be 2 to the power 8 into 2 to the power of 4 into 2 to the power of 1. Now we have seen that like from 2 to the power of 1 we can calculate 2 to the power 2, right? From 2 to the power of 2 we just square it and calculate 2 to the power of 4. Now this will help in our binary exponentiation code. Okay, so the code is like this. I first kept the result as 1. This is the base. Suppose this is 2 and this is 13. Okay. Now, while exponent is greater than 0, what we do is if exponent and 1 equal to 1 means 13 was 1, 1, 0, 1, right? And what we are seeing is if the rightmost bit is set. So if the rightmost bit is set, we take the like 2 to the power of it, right, in the answer. So result is equal to result into the base value percent mod, right? And after this base value is done, we just take the next, go to the next base. So next base will be 2 into 2, which is 4, right? So we just multiply our base for base like 2 into 2 percent mod. Then we just right shift our like number exponent. So 1 1 0 1 will become, in the next step will be 1 1 0. Okay, then the iteration will go for this. Let's look at it. Okay, so we are calculating 2 to the power of 13. Base equal to 2 to the base is 2. Exp is equal to 13, and result initially is 1. This is the initial step setup. Let's go to the first iteration. So exp is 13, so it can be broken as 1 1 0 1. The last bit is set here. Okay, so we take this in our answer, the power of 2 in our answer. So result is equal to 1 into 2 to the power of 1 into 2 is equal to 2 only. Now we calculate the next base here, so which is 2 to the power of 2. So base equal to 2 into 2, like we just multiply 2 into 2, take the square, so equal to 4. So and then we just do a right step operation. So exp is equal to 110. So we will be computing from 110 in the next step. So in the next step we have 110 here. Now we have a 0, this bit is not set, so we don't take the power of 2 in our answer, right? So don't take it. Okay, now what we need to do is we need to take the next base. So here it was like we need to calculate for the next base. From here we have previously we have calculated the base as 4. Now the next base will be 4 into 4 equal to 16, and what we need to do is 1 1 0 will be applied a right shift operation, so it will become 1 1. Okay, now we are computing from 1 1. This particular bit is set, so we need to calculate this particular 2 to the power operation. Okay, so result is equal to 2 into 16. Okay, so equal to 32. This is the like the base we have calculated, and this is the initial result which we have obtained. So result is equal to result into the current 2 to the power, which is 16. And the new base will be for like 1 1 we have. The next time we will calculate for this particular bit, right? So new base for it will be 16 into 16 is equal to 256, and we just make a right shift operation. 1 1 will be broken down to 1 only. Okay, now the fourth iteration here, this bit is set. Okay, so result will be result, the previous result is 32 into the new base which we calculated previously is equal to 256 is equal to 8192. The new base will be, if we had another operation we have to calculate the new base, so base will be 256 into 256, and we have to do a right shift operation, one right shift one times. Okay, so equal to 0. So from this we have calculated the answer in order of log n time. Okay, so let's come back to our code, like question. The algorithm is very simple. Find the max depth of the graph, then the total number of edges will be k, like max depth minus 1. What we need to do is we need to return the power of 2 to the power of k minus 1, and this can be calculated using the binary exponentiation we have discussed. Okay, so here is the pseudocode. So we have been given a edges array, right? So from this edge array we can calculate the graph, like This is very simple. You can go through the code in the comment section. Okay, then after that you can use a BFS or DFS to calculate the height of the graph. Okay, I have like in the code I have used BFS, but you can calculate using the DFS also. Okay, the next step is to calculate the total depth. You can just check this in the code in the comment section. Okay, then the total number of edges will be depth minus 1, and finally just return mod power of 2 comma edges. So this is the binary explanation we have discussed. This will just return this answer. Okay, that's it for this problem. Thanks for watching. If you want more content on LLD, HLD, Gen AI, DSA and software engineering projects, do consider subscribing us. Thank you.